In this lecture, I will answer two questions. On both questions, we find out the area of the shaded region. Let's start with the first question. In the drawing, we have three semicircles. This is the big semicircle that contains those two smaller semicircles. Those two smaller semicircles touch each other externally at this point. We know that the radius of this semicircle is equal to 2 units. The radius of this semicircle equals to 1 unit. Again, our task is to find out the size of this shaded area. So first of all, we define the center of this biggest semicircle. This point is point O. We define the center of this semicircle. This point is point P. We define the center of this small semicircle. This point is point Q. Likewise, we define this is tangent AB. Tangent AB is the diameter of the biggest semicircle. Also, tangent. We define the point of tendency of tangent AB with this medium circle, with this medium semicircle. This point is point M. Likewise, we define the point of tendency of the same tangent AB with this small semicircle. This point is point N. We define the radius of this biggest semicircle as x. So, first of all, we can implement here rule 1. Tangent AB is tangent to this circle at point M. The radius PM of this semicircle is equals to 2. The radius PM is drawn to point M. That is the point of tendency of tangent AB with this medium semicircle. Whenever your radius is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MP. If AB is perpendicular to MP, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to rule 1. Likewise, according to the same rule 1, we have AB is a tangent to this small circle at point N. The radius Qn is equals to 1. The radius Qn is drawn to point N. It is the point of tendency of tangent AB with this small semicircle. Whenever you have radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius NQ. If AB is perpendicular to NQ, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to the same rule 1. We define the touching point of those two semicircles with each other. This point is point T. So those two semicircles touch each other externally at point T. And whenever you have an external mass between two circles or semicircles, you can implement rule 10. So a bit quicker, rule 10. According to rule 10, if two circles touch each other externally, then the straight line that connects the circles together passes through their touching point. In the drawing, we have those two circles that touch each other externally at point P. This is point O, that is the center of this circle. This is point M, that is the center of this circle. and the third line that connects their centers together is of course the third line OM. And according to this rule 10, the third line OM must pass for point P, that is their touching point. Again, the third line OM must pass for their touching point, that is point P. Or OPM is one side line. Again, OPM is one side line according to this rule 10. So again, implement rule 10 in our drawing. Because in our drawing, you have the externals between those two semicircles at point C. Point P is the center of this semicircle. Point Q is the center of this semicircle. The third line that connects the centers together is of course the third line PQ. And according to rule 10, the third line PQ must pass for point T, that is their touching point. Again, the third line PQ must pass for their touching point, that is point T. Or PTQ is one side line. Again, PTQ is one side line according to rule 10. So we join points P and T together by side line, and the third line PQ must pass for point T according to rule 10. You can see here, indeed, the third line PQ passes through point T, that is their touching point, exactly according to rule 10. So PTQ is one side line, and therefore PQ must be equal to PT plus TQ. Okay, because of the fact that PTQ is one side line, it means that PQ in total must be equal to PT plus TQ. So PQ equals to PT. PT is the radius of this semicircle, that is actually 2. Plus TQ. TQ is the radius of this small semicircle, equals to 1. So in total, PQ equals to 2 plus 1, that is 3. PQ equals to 3 units in its length. So it is known, PQ equals to 3, according to rule 10. In the next step, I'll copy this quadrilateral PQNM in a new page, and we'll do a construction on the new drawing. We know that PQ equals to 3, PM equals to 2, QN equals to 1, and side MN of this quadrilateral PQNM is the only missing side. Those two angles, they are both right angles according to rule 1, of course. So actually, this is quadrilateral PQMN that I covered from the original drawing. So, in the next step, we'll do a construction. That is to say, from point Q, from the vertex Q of this quadrilateral PQMN, we will draw perpendicular on PM. Again, from point Q, we will draw perpendicular on PM. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction, of course. We define the touching point of the perpendicular from point Q and PM. This point is point L. So by doing this construction, we get here the small quadrilateral LQ and M. Inside this small quadrilateral LQ and M, we have 1, 2, 3 rectangles, and therefore this 4 pieces angle must be equal to 90 degrees inside, according to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. So in quadrilateral LQ and M, we have 4 rectangles, and therefore it is a rectangle. Quadrilateral LQ and M is a rectangle. But we also know that the opposite sides of rectangle are equal to each other. So in this rectangle LQ and M, side QN must be equal to the opposite side LM. But QN is 1, therefore the opposite side LM must be also equal to 1 unit in its length. LM equals to 1. So what is the length of this missing line thread PL? PL equals to PM minus LM. So PL equals to PM, that is 2, minus LM, that is 1. So in total, PL equals to 2 minus 1, that is 1. PL equals to 1 unit in its length. PL equals to 1. So in the next step, we represent the Pythagoras theorem on this right triangle PLQ. Right triangle PLQ. According to the Pythagoras theorem, in a right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So in the right triangle PLQ, the right triangle PLQ, here by PT is the evaluation for Pythagoras theorem. So in the right triangle PLQ, according to the Pythagoras theorem, PQ squared, that is the square of the hypotenuse, equals to PL squared plus LQ squared. PQ is 3, therefore PQ squared is 3 squared, that is 9, and it is equals to PL squared. PL is 1, therefore PL squared is 1 squared, that is 1, plus LQ squared. LQ is the missing side, so it is. So it is in total, we found out that 9 equals to 1 plus LQ squared. Here we subtract 1 from the equation, and finally get that 9 minus 1 is 8 equals to LQ squared. Here we substitute 8 by 4 times 2, and we get that 4 times 2 equals to LQ squared. Here we take out of this equation, and finally get that the missing side LQ is equal to the square root of 4, that is 2, so inside the root we left only with 2. So in total we should know that LQ equals to 2 times square root of 2 units in its length. This is side LQ equals to 2 times square root of 2 units in its length. We know that the opposite sides of rectangle are equal to each other. So in rectangle LQ and M, side LQ must be equal to the opposite side MN, but LQ equals to 2 times square root of 2, therefore the opposite side MN must be also equal to 2 times square root of 2 units in its length. So this is right side MN that we just right now found out that it equals to 2 times square root of 2 units in its length. So Mn in total equals to 2 times root of 2. We define the length of this line segment MOSA. So what is the length of the missing line segment ON? From the moment, to see that ON in total equals to MN minus MO. So as the norm, the missing line segment ON is equal to MN minus MO. So ON equals to MN. It is given us the question that we just write down found out that MN equals to 2 times root of 2 minus MO. MO equals to A according to our definition. So in total, we actually found out that ON equals to 2 times root of 2 minus A units in its length. In the next step, we'll join points O and Q together by a straight line. Point O is the center of the biggest semicircle. Point Q is the center of this semicircle. Therefore, QF is the radius of this small semicircle that equals to 1. Likewise, we have a QE is of course the radius of this semicircle that equals to 1 unit in its length. So we have here point O that is the center of the biggest semicircle. From the center of the biggest semicircle, that is to say from this point O, we do line segment OQ. Line segment OQ bisects chord EF. Again, line segment OQ bisects chord EF. Why? Because EF in total equals to 2, and at point Q, OQ bisects line segment EF into 2 halves. Each half, of course, equals to 1. The first half, FQ is 1, and the second half, QE is also 1. So from the center of this big semicircle, that is to say from this point off, we have line segment OQ that bisects chord EF. And whenever you have a line segment that is drawn from the center of the circle and bisects any chord, it will be also perpendicular to that chord. According to rule 30, of course. So repeat quickly on rule 30. According to rule 30, a line segment that is drawn from the center of a circle and bisects a chord will be also perpendicular to that chord. So in the drawing, we have a circle. Point O is the center of this circle. AB is the chord in this circle. From point O, we draw line segment OM that bisects chord AB. Again, line segment OM bisects chord AB. That is to say, AM equals to MB equals to AB over 2. And because of the fact that OM bisects chord AB, OM will be also perpendicular to chord AB. If OM is perpendicular to AB, it means that this angle equals to 90 degrees, and this angle equals to 90 degrees according to this rule, rule 30. So we can definitely implement rule 30 in our drawing. Why? Because in our drawing, as I mentioned before, from the center of this biggest semicircle, that is to say from point O, we have line segment OQ that bisects chord EF. And therefore, according to rule 30, line segment OQ will be also perpendicular to chord EF. If OQ is perpendicular to EF, it means that this angle equals to 90 degrees, and this angle must be also equal to 90 degrees in its side according to rule 30. In the next step, we will join points Q and D together by a straight line. What is the definition of line segment QE? Line segment OE. Line segment OE starts from the center of the biggest semicircle and ends at a point that is a point on the biggest semicircle itself. So this is exactly the definition of a radius. Therefore, OE is the radius of the biggest semicircle is equal to x according to our definition. So that is known that right side OE equals to x, that is the radius of the biggest semicircle according to our definition. So, in the next step, we will implement the Pythagoras theorem on this green right triangle EOEQ. Okay. So we have, according to the Pythagoras theorem, in a right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So in this right triangle EOQ, the hypotenuse is EO. So EO squared, that is the square of the hypotenuse, is equal to EQ squared plus QO squared. And again, in this green right triangle EQO, according to the Pythagoras theorem, EO squared, that is the square of the hypotenuse, equals to EQ squared plus QO squared. EO squared, that is the square of the hypotenuse, equals to EQ squared plus QO squared. EO is x, therefore EO squared is x squared. And it is equals to EQ squared. EQ is 1, therefore EQ squared is 1 squared, that is 1. Plus QO squared. QO is the hypotenuse of this right triangle QNO. Again, QO is the hypotenuse of this right pink triangle QNO. And therefore, according to the Pythagoras theorem, if we implement the Pythagoras theorem on this pink triangle QNO, we get that QO squared equals to QN squared plus NO squared. And again, QO is the hypotenuse of this pink triangle, and therefore, according to the Pythagoras theorem, if we implement the Pythagoras theorem in this pink right triangle QNO, we get that QO squared equals to QN squared plus NO squared. So EQ squared, EO squared equals to EQ squared plus QO squared. EQ is x, therefore EO is x, therefore EO squared is x squared, and it equals to EQ squared. EQ is 1, therefore EQ squared is 1 squared, this is 1. QO squared. QO squared equals to QN squared plus NO squared. So QO squared equals to QN squared plus NO squared. So we found out that according to equation 1, x squared equals to 1 plus QN squared plus NO squared. So x squared equals to 1 plus Qn squared. Qn is also 1, therefore Qn squared is 1 squared, that is 1 plus NO squared. NO equals to 2 times square root of 2 minus 8, therefore NO squared equals to 2 times square root of 2 minus 8 squared. Okay, again, if we found out that x squared equals to 1 plus 1, plus 2 times of 2 minus a squared. So x squared equals to 1 plus 1, that is 2, plus, we'll open the brackets of this expression, 2 times square root of 2 minus a squared equals to 2 times square root of 2 squared, that is 8, plus a squared minus 2 times square root of 2, a. So in total, according to equation 1, we found out that x squared equals to 2 plus 8 is 10 minus a squared. Here minus 2 times 2 is minus 4, so in total this expression equals to minus 4 times square root of 2 times a. So in total, according to equation 1, if we found out that x squared equals to 10 minus a squared minus 4 times square root of 2 times a. This is according to equation 1. In the next step, we repeat on the same process that we did here on this side of the bigger semicircle. That is to say, we'll join points O and P together by straight line. So OP is a line segment that is drawn from the center of the biggest semicircle, that is to say from this point O towards chord CD. Again, line segment OP is drawn from the center of the biggest semicircle to chord CD. Point P is the center of this semicircle, therefore PC is the radius of this semicircle equals to 2. Likewise, PD is also the radius of the semicircle, that was to 2. So actually, this is chord CD. Chord CD in total equals to 2 plus 2, that is 4. So at point P, line segment OP bisect chord CD. Again, line segment OP bisect chord CD. The first half of chord CD is CP, that is 2. The second half is PD, that also equals to 2. And because of the fact that from the center of this biggest semicircle, that is to say from point O, we have line segment OP that bisects chord CP. Line segment OP will be also perpendicular to this chord CD according to Rule 30. Okay. So therefore, this angle equals to 90 degrees on its side, and this angle also equals to 90 degrees on its side according to Rule 30. So in the next step, we will join points O and C together by a straight line. What is the definition of line segment OC? Line segment OC starts from point O, that is the center of the biggest semicircle, and ends at point C, that is the point of the biggest semicircle itself. So this is exactly the definition of a radius. Therefore, OC is the radius of the biggest semicircle, this is equals to x. OC equals to x. So, in the next step, We'll implement the Pythagoras theorem on this green right triangle CPO. So according to the Pythagoras theorem on this green triangle CPO, CO squared, that is the square of the hypotenuse, equals to CP squared plus PO squared. And again, according to the Pythagoras theorem, on this green triangle CPO, CO squared, that is the square of the hypotenuse, equals to CP squared plus PO squared. CO equals to x, therefore CO squared is x squared. And it is equals to CP squared. CP is 2, therefore CP squared is 2 squared, that is 4. Plus PO squared. What is the value of PO squared? PO is the hypotenuse of this triangle PMO. Again, PO is the hypotenuse of this triangle PMO. This is tangent PO, that is the hypotenuse of this pink triangle PMO. And therefore, according to the Pythagoras theorem, PO squared will be equal to PM squared plus MO squared. So PO squared equals to PM squared plus MO squared. We found out that CO squared equals to CP squared plus PO squared. CO is x, therefore CO squared is x squared. CP is 2, therefore CP squared is 2 squared, that is 4. PO squared equals to PM squared plus OM squared. Why? Because PO squared is the square of the hypotenuse of this pink triangle PMO. And according to the Pythagoras theorem, if you implement the Pythagoras theorem on this pink triangle PMO, PO squared will be equal to PM squared plus MO squared. So in total, we found out that x squared equals to 4 plus PM squared. PM is 2, therefore PM squared is 2 squared, that is 4, plus MO squared. MO is 8, therefore MO squared is 8 squared. So in total, according to equation 3, according to equation 2, we found out that x squared equals to 4 plus a squared. So x squared equals to 4 plus 4 is 8 plus a squared. So according to equation 2, we should find out that x squared equals to 8 plus a squared. This is according to equation 2. And according to equation 1, we only found out that x squared equals to 10 minus a squared, actually 10 plus a squared, 10 plus a squared minus 4 times square root of 2 times a. So we have two different equations for x squared, equation 1 and equation 2. Therefore, we create equation 3. It says that x squared according to equation 1 must be equal to x squared according to equation 2. x squared according to equation 1 equals to 10 plus a squared minus 4 times square root of 2 times a, and it must be equal to x squared according to equation 2. X squared according to equation 2 equals to 8 plus a squared. So total according to equation 3, we have found out that 10 plus a squared minus 4 times square root of 2 times a equals to 8 plus a squared. We have a squared on both sides of this equation, so a squared will get cancelled. So here we subtract 8 from this equation, equation 3, and finally we get that according to equation 3, 10 minus 8 is 2, minus 4 times square root of 2 times a equals to 0. So here we read 4 times square root of 2 times a to this equation, and get that according to equation 3, 2 equals to 4 times square root of 2 times a. Here we will divide this equation 3 by 2, and finally get that according to equation 3, 2 over 2 is 1 equals to 4 over 2 is 2, so in total this expression equals to 2 times square root of 2 times a. So 1 equals to 2 times square root of 2 times a. Here we will divide this equation 3 by 2 times square root of 2, and finally get that a, according to equation 3, a equals to 1 over 2 times square root of 2. So it's in its length. Okay, this is line 7 to m, this equals to a, and a equals to 1 over 2 times square root of 2 units in its length. According to equation 2, we found out that x squared equals to 8 plus a squared. So x squared equals to 8 plus a squared. A is 1 over 2 times square root of 2, and therefore a squared must be equal to 1 over 2 times square root of 2 squared, that is 8. So in total, we found out that x equals to 8 plus 1/8. So x squared equals to 8 plus 1/8. So x squared equals to 1/8. Here we will multiply 8 by 8 and then we divide it by 8 in order to account factor with this number. And get that 8 times 8 is 64 divided by 8. We multiply it by 8 and then divide it by 8, so we change nothing. So to that, we found out that x squared equals to 64 plus 5, 64 plus 1 is 65 over 8. So total according to equation 2, we found out that x squared equals to 65 over 8. So our test is to find out the area of the green shape. So So we have to find out the area of this shaded region. And again, we have to find out the area of this shaded region. From the drawing, it's very easy to see that the area of the shaded region in total must be equal to the area of the biggest semicircle plus the sum of the rest of those two semicircles. Again, the size of this shaded area must be equal to the area of the biggest semicircle minus the sum of the rest of those two semicircles. Okay, write it down. The size of this shaded area. That is the area that we are looking for in this question. It must be equal to the area of the biggest semicircle minus the area of the right semicircle minus the area of the left semicircle. It's very easy to see from the drawing that if you subtract from the area of this biggest semicircle those two areas, you will get the shaded area. Very simple. So the shaded area equals to the area of the biggest semicircle. What is the area of this biggest semicircle? We know that the radius of this biggest semicircle is x, therefore the area must be equal to pi x squared over 2. The area of the biggest semicircle must be equal to pi x squared over 2 because x is the radius. Minus the area of this right semicircle, we know that the radius of this semicircle equals to 1, and therefore the area must be equal to pi times 1 square over 2. Pi times 1 square over 2. Minus the area of this left semicircle, the radius of this left semicircle is 2, therefore the area of this left semicircle must be equal to pi 2 square over 2. Pi 2 square over 2. So here, found out that the value of the shaded area equals to pi x square minus pi 1 square over 2 minus pi 2 square over 2. Here we take pi over 2 as a common factor out of those three expressions. So inside the bracket we left here with x squared minus 1 squared, that is 1, minus 2 squared, that is 4. So in total, the area of the shaded region, the size of the shaded region equals to pi over 2. X squared is 65 over 8, minus 1 minus 4 is minus 5. So it is pi over 2. We have 65 over 8 minus 5. So here we multiply minus 5 by 8 and then divide it by 8 in order to a common factor with this number. And we get that 65 over 8, and minus 5 times 8 is minus 40 divided by 8. So we have pi over 2, 65 minus 40 is 25 over 8. So the denominator we have 25 pi over 2 times 8 is 16. So the size of the shaded area equals to either 25 pi over 16 square units in its size, or in terms of numbers, it is equal to 4.09 square units in its size. Repeat again, I should hold on that the size of this shaded area equals to, in total, either 25 pi over 16 square units in its size, or in terms of numbers, it is equals to 4.09 square units in its size. So we finished to answer the first question. In the next step, I will present you the second question and solve the second question of this lecture. In this second question, our task is to find out the size of this shaded area. What is the shaded area? Is the area of this small semicircle. So we have to find out the area of this small semicircle, the shaded area. So in the drawing, we have two semicircles that intersect with each other, those 2 points, and then they touch each other here. You know that this is line 7 AM, that is equals to 3 units in itself. This is line 7 MN, that is also equals to 4 units in itself. This is line 7 NB, that is equals to 2 units in its length. Again, our task is to find out the size of this small semicircle. The area of this small semicircle is the shaded area. So first of all, we know that AB is the diameter of this big semicircle. AB in total equals to 3 plus 3 plus 2. Again, AB in total equals to AM, that is 3, plus MN, that is also 3, plus MB, that is 2. So in total, AB equals to 3 plus 2, that is 8. The diameter of this big semicircle equals to 8 units in its length. So it is known. The diameter AB of the big semicircle equals to 3 plus 3 plus 2, that is 8. AB equals to 8. So we define the radius of this big semicircle as R. So the radius R must be equal to the diameter AB over 2. AB is 8, so it is 8 over 2, that is 4. So the radius of this big semicircle, the radius R equals to 4 units in its length. R equals to 4. In the next step, we find the center of this big semicircle. This point is point O. Likewise, we define the center of this small semicircle. This point is point S. What is the length of this line 7? Line 7 MO. MO equals to AO minus AM. So it is now MO, the short line 7 MO, equals to AO minus AM. So MO in total equals to AO. AO is the radius of this big semicircle, that is 4. Minus AM is 3 according to what is given us the question. So in total, MO equals to 4 minus 3, that is 1. MO equals to 1 unit in its length. In the next step, we will do a construction, that is to say, from the center of this small semicircle, that is point S, we will go a line segment that bisects chord MN. Again, from point S, we will go a line segment that bisects chord MN. Chord MN is a chord inside this small semicircle, of course. So from point S, we will go a line segment that bisects chord M. Actually, from point S, we will go perpendicular on chord MN. Again, from point S, we will go perpendicular on chord MN. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point S and MN. This point is point T. Okay, so this is the perpendicular of chord MN according to our construction. We define the length of side ST, SH. So from the center of this small semicircle, we draw a line segment that bisects chord MN. So here we can implement rule 30. Repeat quickly rule 30. According to rule 30, a line segment that is drawn from the center of a circle and bisects the chord will be also perpendicular to that chord. In the moment we have a circle, point O is the center of the circle. From the center of the circle, this is to say from this point O, we draw line segment OM that bisects chord AB. Again, line segment OM bisects chord AB according to our construction. If line segment OM bisects chord AB, it means that AM equals to MB equals to AB over 2. And because of the fact that line segment OM bisects chord AB, line segment OM will be also perpendicular on AB. OM is perpendicular to AB. If OM is perpendicular to AB, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to this rule 30. So whenever you draw from the center of the circle a line segment that bisects a chord, that line segment will be also perpendicular to that chord. This is according to rule 30. So we can implement rule 30 in our drawing. What is in our drawing? From point S, that is the center of this semicircle, we draw actually it is not rule 30 but rule 15. Again, from line segment from point S we go perpendicular on MN. So here we can implement rule 15. According to rule 15, a perpendicular from the center of a circle to any chord bisects the chord. So in the line we have a circle, point S is the center of the circle. From point S we do perpendicular ST on chord MN. Again, from point S, that is the center of the circle, we do perpendicular ST on MN. So this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to our construction. So perpendicular ST also bisects chord MN. If ST bisects chord MN, it means that MT equals to TN equals to MN over 2. Again, MT equals to TN and it equals to MN over 2. So we can implement rule 15 in our drawing. What put in our drawing? From point S, that is the center of this semicircle, we do perpendicular OT on chord MN. And therefore, according to rule 15, perpendicular ST bisects chord MN. If ST bisects chord MN, it means that MT equals to TN. MT equals to TN. MT equals to TN. So MT equals to Tn, and line segment MN has been bisected into two halves. Each half must be equal to MN over 2. The first line segment MN has been bisected by ST. So the first half MT must be equal to the second half Tn, and each half must be equal to Mn over 2 because Mn has been bisected. So the first half MT must be equal to the second half Tn, and each half of course must be equal to Mn over 2 according to rule 15. Mn is 3, therefore Mn over 2 is 3 over 2, that is 1.5. So in total, note that MT equals to Tn equals to 1.5 units. Okay, MT equals to Tn equals to 1.5 units. This is line segment MT is equals to 1.5 units. This is line 17. This is also equal to 1.5 units according to rule 15. Okay, so what is the length of this short line segment? Line segment OT. OT equals to MT minus MO. Again, MT minus MO equals to OT. So write it down. The short line segment OT in total equals to MT minus MO. And again, the length of the short line segment MT, the length of the short line segment OT equals to MT minus MO. So OT, the short line segment OT equals to MT. MT is 1.5 minus MO. MO is 1. So in total OT equals to 1.5 minus 1 is 1 half. So OT equals to 1 half. This is the short line segment OT equals to 1 half units in its length. In the next step, we will join points O and S together by straight line. That is to say, we will join the centers of those two semicircles with each other by straight line. Point O is the center of the big semicircle. Point S is the center of this small semicircle. SQ is the radius of this small semicircle. We define the radius of this small semicircle Sx, so SQ equals to x. Likewise, SP is also the radius of this small semicircle. It equals to x. So from point O, that is the center of this big semicircle, we draw line segment OS that bisects chord PQ. Why OS bisects chord PQ? Because PQ is the diameter of this small semicircle that equals to 2x. At point S, OS bisects PQ into 2 halves. Each half equals to x, of course. PS equals to x and SQ equals P, SQ also equals to x. So from the center of this big semicircle, we draw line segment OS that bisects chord PQ. Again, from the center of this big semicircle, we draw line segment OS that bisects this chord PQ. And whenever you draw from the center of any circle a line segment that bisects the chord, then you can implement rule 30. Please click on rule 30. According to rule 30. A line segment that is drawn from the center of a circle and bisect a chord will be also perpendicular to that chord. So mentioned in the first question. In the drawing we have a circle, point O is the center of the circle. We have, this is chord AB, and from point O that is the center of this circle, we draw line segment OM that bisects chord AB. Again, line segment OM bisects chord AB according to our construction. That is to say, AM equals to MB equals to AB over 2. And because of the fact that line segment OM bisects chord AB, line segment OM will be also perpendicular to AB. If OM is perpendicular to AB, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to this rule 30. So whenever you go from the center of a circle or semicircle, a line segment that bisects a chord, then that line segment will be also perpendicular to that chord. Here, line segment OM bisects chord AB, therefore line segment OM will be also perpendicular to AB. That is to say, this angle equals to 90 degrees, and this angle equals to 90 degrees according to this rule 30. So we can implement rule 30 in our drawing. In our drawing, from the center of this big semicircle, that is to say from this point O, we draw line segment OS that bisects chord PQ. And according to rule 30, Right side OS will be also perpendicular to PQ. If O is perpendicular to PQ, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to Rule 30. So in the next step, we define the length of line segment OS as y, and we'll implement the Pythagoras theorem on this right triangle OST. So copy the right triangle OST in the equation, we'll implement on it the Pythagoras theorem. So clearly this is the right triangle OST that I come from the original drawing. In this right triangle OST, according to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So in this right triangle OST, SO squared, that is the square of the hypotenuse, equals to ST squared plus TO squared. So I write it down. This will be equation 1. So SO squared, that is the square of the hypotenuse, is equal to ST squared plus OT squared. SO is y, therefore SO squared is y squared, and it equals to ST squared. ST is 1/2, therefore ST squared is 1/2 squared, that is 1/4, plus ST squared. ST is h, therefore ST squared is h squared. So in total, according to equation 1, we actually found out that y squared equals to 1/4 plus h squared. So according to equation 1, we actually found out that y squared equals to h squared plus 1/4. So in the next step, we will join points S and N together by side line. Point S is the center of this small semicircle, point N is the point of the small semicircle itself. Therefore, Sn is the radius of this small semicircle, equals to x. So in the next step, I copy the right triangle TSN in the equation. We will implement on this right triangle STN the Pythagoras theorem. Tn equals to 1.5 units in its length. The hypotenuse Sn equals to x. Okay, this is right angle STN, the comes from the original domain. This right angle STN, Sn squared, that is the square of the hypotenuse, is equal to St square plus Tn square. Sn is x, therefore Sn square is x squared. And it equals to St square. St is h, therefore St square is h squared plus Tn square. Tn is 3 over 2, therefore Tn square is 3 over 2 square. That is 9 quarters. So in total, according to equation 2, we actually found out that x square equals to h square plus 9 quarters. This is according to equation 2, and according to equation 1, we only found out that y squared equals to h squared plus 1 quarter. So here, two equations. X squared equals to h squared plus 9 quarters, and y squared equals to h squared plus 1 quarter. Here we subtract equation 1 from equation 2. We get the equation 3 that says that x squared minus y squared equals to h squared plus 9 quarters minus h squared plus 1 quarter. So this h squared plus 9 quarters. We'll open the brackets here, it will be minus h squared minus 1 quarter. So here h squared minus h squared is 0. H squared minus h squared is 0, and 9 quarters minus 1 quarter is 8 quarters. 8 quarters is 2. So in total, we found out that according to equation 3, x squared minus y squared equals to 2. This is according to equation 3. In the next step, we will join points O and P together by straight line. Point O is the center of the big semicircle, point P is the point of the big semicircle itself. Therefore, OP is the radius of this big semicircle, that equals to 4 units in its length, according to what we already found out. So in the next step, we'll implement the Pythagoras theorem on this triangle, right triangle OSP. So copy the right triangle OSP in your page, and we'll implement on it the Pythagoras theorem. Okay, this is the right angle PSO that is coming from the original drawing. In this right angle PSO, P all squared, that is the square of the hypotenuse, equals to PS squared plus SO squared. So PO is 4, therefore PO squared is 4 squared, that is 16. And it equals to PS squared. PS is x, therefore PS squared is x squared plus SO squared. SO is y, therefore SO squared is y squared. So in total, according to equation 4, we should find out that x squared plus y squared equals to 16. This is according to equation 4. Well, according to equation 3, we already found out that x squared minus y squared equals to 2. So here we will add equation 4 to equation 3. So we get that x plus x is x squared plus x squared is 2x squared. Y squared minus y squared is 0 equals to 16 plus 2 is 18. So 2x squared equals to 18. Then we divide the equation 5 by 2 and finally get that according to equation 5, x squared equals to 18 over 2 is 9. So x squared equals to 9. Our task is to find out the size of this shaded area. What is the shaded area? It is actually the area of this small semicircle. The radius of this small semicircle is x, and therefore the area must be equal to pi x squared over 2. So the size of the shaded area is pi x squared over 2. That is actually the area of this small semicircle, that is radius is x, and therefore the area must be equal to pi x squared over 2. So it is pi over 2 times x squared. X squared is 9, so we solve x squared by 9. We get that the size of the shaded area in total equals to 9 pi over 2. 9 over 2 is 4.5, so it is 4.5 pi. 4.5 pi is equal to 14.137 square meters in its size. And again, we found out that the area that we are looking for in this question, this is the size of this shaded area. In total, it is equal to either 4.5 pi square meters in size, or in terms of numbers, it is equal to 14.137 square meters in size. So we finished to answer the second question. In the next step, I will start the lecture. We'll start with the first question, of course. In this first question, our task is to find out the area of this shaded region. So in the drawing, we have 3 semicircles. This is the biggest semicircle that contains those 2 small semicircles. Those 2 small semicircles touch each other somewhere at this point. We know that the radius of this semicircle is equal to 2 units. The radius of this small semicircle equals to 1 unit. Again, our task is to find out the size of this shaded area. So first of all, we defined the center of this semicircle. This point is point P. Likewise, we define the center of this small semicircle. This point is point Q. We define the point of tendency of AB with this semicircle. This point is point M. Likewise, we define the point of tendency of AB with this semicircle, small semicircle. This point is point N. PM is the radius of this semicircle, that is equals to 2. The radius PM is equals to 2. The radius PM is on to point M, that is the point of tendency of tangent AB with this semicircle. And whenever your radius that is on to the point of tendency, then tangent AB will be perpendicular to the radius MP. If AB is perpendicular to MP, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to all 1. Likewise, according to the sum all 1, the radius Qn equals to 1, the radius Qn of this semicircle is on to point N, the point of tendency of tangent AB with this small semicircle. And whenever your radius is on to the point of tendency, then tangent AB will be perpendicular to the radius NQ. If AB is perpendicular to NQ, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the sum all 1. So, in the next step, we implemented rule 10 in our drawing. We define the touching point of those two semicircles with each other. This point is point T. Whenever you want to examine between two circles or semicircles like here, you can implement rule 10. So implement rule 10. According to rule 10, if two circles touch each other externally, then the straight line that connects the circles together passes through their touching point. So in the drawing, those two circles touch each other externally at point P. The center of this circle is at point O. The center of this circle is at point M. The straight line that connects the circles together is of course the straight line OM. And this straight line OM must pass for point P, that is their touching point. Again, the straight line OM that connects the circles together must pass for their touching point, that is point P. Or OPM is one straight line. Again, OPM is one straight line according to this rule 10. So we can implement rule 10 in our drawing. Also in our drawing, those two circles touch each other, those two semicircles touch each other externally at this point T. The center of this semicircle is at point P. The center of this small semicircle is at point Q. The straight line that connects the circles together is of course the straight line PQ. The straight line PQ must pass for point T, that is their touching point. Again, the straight line PQ must pass for their touching point, that is point T. Or PTQ is one straight line. Again, PTQ is one straight line according to rule 10. If PTQ is one straight line, it means that PQ in total must be equal to PT plus TQ. That is to say, PQ in total equals to PT, that is 2, that is the radius of this semicircle, plus TQ, that is 1, it is the radius of this small semicircle. So in total, PQ must be equal to 2 plus 1, that is 3, and PQ equals to 3 in its length. The next step, I copied this quadrangle PM and Q in the new page, and actually did the construction in the new drawing to this quadrangle PM and Q. This is quadrangle PMQN, the control drawing. And again, this is quadrangle PM and Q, the control drawing. So from point Q, we do perpendicular on PM. Again, from point Q, we do perpendicular on PM. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point Q and PM. This point is point A. By doing this construction, we can derive quadrangle QLMN. In quadrangle QLMN, we have 1, 2, 3 degrees, and therefore this fourth angle must be equal to 90 degrees in size according to the rule that says that the sum of the angles in any quadrangle is equal to 360 degrees. So in quadrangle QLMN, we have 4 angles, and therefore it is a rectangle. But we also know that the opposite sides of the rectangle are equal to each other. So in rectangle QLMN, side LM must be equal to the opposite side QN. But LM is 1, therefore the opposite side QN must be also equal to 1 unit in its length. What is the length of this line segment LP? LP equals to LM LP equals to PM minus LM. Or PL equals to PM minus LM. PL equals to PM minus LM. So PL equals to PM, that is 2, minus LM, that is 1. So total PL equals to 2 minus 1, that is 1. PL equals to 1 unit in itself. So in the next step, I copied this green, I implemented the Pythagoras theorem on this green triangle PLQ. According to the Pythagoras theorem, in a triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So in this green triangle PLQ, PQ squared, that is the square of the hypotenuse, equals to PL squared plus LQ squared. PQ is 3, therefore PQ squared is 3 squared, that is 9, and it equals to PL squared. PL is 1, therefore PL squared is 1 squared, that is 1, plus LQ squared. LQ is the missing side, so in total, if you found out that 9 equals to 1 plus LQ squared. Here we subtracted 1 from this equation, if I found out that 9 minus 1 is 8 equals to LQ squared. Here we substituted 8 by 4 times 2, so 4 times 2 equals to LQ squared. Here we took out of this equation, and I found out that LQ equals to the square root of 4, that is 2, so inside the root we left only with 2. So in total, LQ equals to 2 times square root of 2 units in itself. So in after get LQ and M, the opposite sides are equal to each other. So side LQ must be equal to the opposite side MN. But LQ equals to 2 times square root of 2, therefore the opposite side MN must be also equal to 2 times square root of 2 units in itself. This is nice with MN, that is just side now found out, that is equals to 2 times square root of 2 units in itself. We define the length of MO as A, and therefore ON must be equal to MN minus OM. Again, ON equals to MN minus OM. So ON, this is the missing answer, and ON equals to MN, that is 2 times square root of 2, minus ON, that is 8. So in total, ON equals to 2 times square root of 2, minus ON is in its length. In the next step, we join points O and Q together by straight line. Point O is the center of the biggest semicircle. This is called EF. Called EF in total equals to 2 units. EF is actually the diameter of this small semicircle. The radius of this small semicircle is 1, therefore the diameter EF must be equal to 2. Point Q is the center of this small semicircle, therefore Q is the radius of this small semicircle, that is 1. Likewise, QF is also the radius of this small semicircle, that is 1. So it's point Q or Q bisect EF. Again, it's point Q or Q, line segment OQ bisect for EF. And because of the fact that from the center of the circle we have line segment OQ that bisect chord EF, line segment OQ must be also perpendicular to chord EF. According to Rule 30. Repeat with Rule 30. According to Rule 30, a line segment that is drawn from the center of the circle and bisect the chord will be also perpendicular to that chord. In the drawing, we have a circle, this is point O, that is the center of the circle. This is called AB. Line segment OM bisects chord AB according to our construction. Again, line segment OM bisects chord AB according to our construction. And therefore, line segment OM will be also perpendicular to chord AB. If OM bisects AB, then OM must be perpendicular to AB. So OM is perpendicular to AB according to this Rule 30. That is to say, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to Rule 30. So whenever you have a line segment that is drawn from the center of the circle and bisects the chord, then that line segment will be also perpendicular to that chord. For the initial form, we can implement Rule 30 in our drawing. From the center of this biggest semicircle, that is to say from point O, we have line segment OQ that bisects chord EF. And therefore line segment OQ must be also perpendicular to EF. If OQ is perpendicular to EF, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to Rule 30. In the next step, we join points O and D together by straight line. Point O is the center of this biggest semicircle. Point E is the point on the biggest semicircle itself. Therefore, O is the radius of this biggest semicircle equals to X according to our definition. So in the next step, we implemented the Pythagoras theorem on this green triangle OE, on this green right triangle OEQ. According to the Pythagoras theorem, on this big right triangle OEQ, OE squared, that is the square of the hypotenuse, equals to EQ squared plus QO squared. Repeat again according to the Pythagoras theorem on this green triangle OEQ. EO squared, that is the square of the hypotenuse, equals to EQ squared plus QO squared. EO is x, therefore EO squared is x squared, and it is equals to EQ squared. EQ is 1, therefore EQ squared is 1 squared, that is 1 plus QO squared. What is the definition of QO? QO is one side of the green right triangle EQO, but QO is also the hypotenuse of the pink triangle QNO. Again, QO is also the hypotenuse of the pink triangle QNO. Therefore, QO squared, according to the Pythagoras theorem, if we implement the Pythagoras theorem on the pink triangle QNO, we get that QO squared equals to QN squared plus NO squared. So, but before that, actually, okay, so this is on QO. So, QO square equals to QN square plus NO square. And again, QO square equals to QN square plus NO square. QO square equals to QN square plus NO square. So in total, x square equals to 1 plus QN square. QN is 1, therefore QN square is 1 square, plus NO square. NO is 2 times root of 2 1 side, therefore NO square is 2 times root of 2 times 2 times root of 2 1 side square. So in total, we should find out that x square equals to 1 plus 1 plus 2 times root of 2 1 side square. So x square equals to 1 plus 1, that is 2. You open the brackets of this expression. 2 times root of 2 1 a square equals to 2 times root of 2 squared, that is 8, plus a square plus 2 times 2 times root of 2 times a. So x square equals to 2 plus 8, that is 10, and we have a square plus a square. 2 times 2 is minus 2 times 2 is minus 4, so in total this expression equals to minus 4 times root of 2 times a. So in total, according to equation 1, we shall find out that x square equals to 10 plus a square minus 4 times root of 2 times a. Repeated on the same process here. On this side of the bigger semicircle. So if we join points O and P together by a straight line, join points O and P together by a straight line. Line side OP, that is all from the center of this biggest semicircle, this is point O, line side OP bisects chord CD. Why OP bisects CD? Because CD is the diameter of this semicircle, that is in total 4. At point P, line side CD is the midpoint of at point P. Actually, CD, point P is the midpoint of CD. And therefore, at point P, chord CD is bisected into 2 halves. The first half CD is 2, the second half PD is also 2. So, from the center of this biggest semicircle, that is to say from point O, line center OP, that bisects chord CD. Therefore, according to Rule 30, line center OP will be also perpendicular to CD. If OP is perpendicular to CD, it means that this angle equals 90 degrees, and this angle also equals 90 degrees, according to Rule 30. So, in the next step, we join points O and C together by a straight line. Point O is the center of this biggest semicircle, point C is the point of the biggest semicircle center, therefore OC is the radius of this biggest semicircle, that is x. In the next step, we implemented the Pythagoras theorem on this right triangle CPO. This right triangle CPO, CO squared, that is the square of the hypotenuse, equals to CP squared plus PO squared. Again, the right triangle CPO, according to the Pythagoras theorem, CO squared, that is the square of the hypotenuse, equals to CP squared plus PO squared. CO is x, therefore CO square is x squared, and it is equals to CP squared. CP is 2, therefore CP squared is 2 squared, plus PO squared. PO is one side of this CPO, but PO is the hypotenuse of the big triangle. PO is the hypotenuse of the big triangle PMO, therefore PO square must be equal to PM square plus MO square. And again, PO square must be equal to PM square plus OM square, because this is the hypotenuse of the big triangle PMO. Therefore it is equal to PM square plus MO square. So in total, X square equals CO equals to X, and therefore CO square equals to X square, CP equals to 2, therefore CP square equals to 2 square, that is 4, and PO square is equals to PM square plus MO square. So X square equals to 4, and here PM is 2, therefore PM square is 2 square, plus MO square. MO is 8, therefore MO square is 8 square. So in total, we should find out that X square equals to 4 plus 8 square. So X square equals to 4 plus 4 is 8 plus 8 square. X square equals to 8 plus 8 square. This is according to equation 2, and according to equation 1. We only found out that X square equals to 10 plus 8 square plus 4 times square root of 2 times 8. So we have two different equations for X square. Therefore we created equation 3 that says that X square according to equation 1 must be equal to X square according to equation 2. X square according to equation 1 equals to 10 plus 8 square minus 4 times square root of 2 times 8, and it must be equal to X square according to equation 2, that equals to 8 plus 8 square. So in total, according to equation 3, I should find out that 10 plus 8 square minus 4 times square root of 2 times 8 equals to 8 plus 8 square. Here we have 8 square on both sides of the equation, so 8 square will get cancelled. Here substitute 8 from this equation, and found out that 10 minus 8 is 2, minus 4 times square root of 2 equals to 0. Here we did 4 times square root of 2 times 8 to this equation, and we found out that 2 equals to 4 times square root of 2 times 8. Here we divided this equation 3 by 2, and so we found out that 2 over 2 is 1, equals to 4 over 2 is 2, so this expression equals to 2 times square root of 2 times 8. So 1 equals to 2 times square root of 2 times 8. Here we divided this equation 3 by 2 times square root of 2, and we found out that A equals to 1 over 2 times square root of 2 units in its length. According to equation 2, we only found out that X square equals to 8 plus 8 square, so X square equals to 8 plus 8 square. A is 1 over 2 times square root of 2, and therefore A square is 1 over square root of 2 times 1 over 2 times square root of 2 squared, that is 8. So in total, A square equals to 1/8. So X square equals to 8 plus 1/8. So X square equals to 8 and 1/8. So we multiplied 8 by 8, and then we divided by 8 in order to come out of this number. And we found out that 8 times 8 is 64 divided by 8. So 64 plus 1 is 65 over 8. So in total, we found out that X square equals to 65 over 8. This is according to equation 2. Our task is to find out the size of this shaded area. From the drawing, it is very easy to see that the size of this shaded area in total must be equal to the size of the biggest semicircle minus the sum of this, minus the sum of the areas, minus the sum of those two areas. Again, the size of this shaded area must be equal to the size of this big semicircle minus the sum of the areas of those two smaller semicircles. Again, the shaded area equals to the area of the big semicircle minus the sum of those two small semicircles. Okay. So the size of the shaded region in total must be equal to the area of the biggest semicircle minus the area of the right semicircle minus the area of the left semicircle. The area of the biggest semicircle, the radius of the biggest semicircle is x, therefore the area must be equal to pi x squared over 2 minus the area of the right semicircle. The radius of the right semicircle is 1, therefore the area must be equal to pi times 1 square over 2. Also the area of the left semicircle, the radius of the left semicircle is 2, therefore the area of the left semicircle must be equal to pi times 2 square over 2. So here we took pi over 2, the second factor out of those three expressions. So inside the brackets we have x squared minus 1 minus 4. X squared is 65 over 8. Minus 1 minus 4 is minus 5. So here multiplied minus 5 by 8 and then we divided by 8 in order to come up with this number. So minus 5 times 8 is minus 40 divided by 8. So in total we should know that the size of the shaded area equals to pi over 2 times 65 minus 40 over 8. 65 minus 40 is 25 divided by 2 times 8, that is 16. So in total we should find out that the size of this shaded area equals to either 25 pi over 16 square units in size, or in terms of numbers it is equals to 4.09 square units in size. So we finished to repeat on the first question. The next step, repeat on the summary, repeat on the solution of the second question. In the second question, our task was to find out the size of this shaded area. The shaded area is inside this small semicircle. So we need to find out the area of this small semicircle. So in the drawing we have those two semicircles. You know that line segment AM equals to 3 units in its length. Line segment MN equals to also 3 units in its length. Line segment NB equals to 2 units in its length. Again, our task is to find out the size of this shaded area. This is actually the size of this small semicircle. AB is the diameter of this big semicircle. AB in total equals to AM, that is 3, plus MN, that is also 3, plus NB, that is 2. So in total, AB equals to 3 plus 3 plus 2, that is 8. AB equals to 8. The diameter of the big semicircle is 8, and therefore the radius must be equal to the diameter over 2. The radius R must be equal to AB over 2. So the radius R of the big semicircle must be equal to AB over 2, that is 8 over 2, that is 4. The radius of this big semicircle equals to 4 units in its length. MO equals to AO minus AM. So MO equals to AO minus AM, MO equals to AO. AO is the radius of this big semicircle, that is 4, because O is the center of this big semicircle and S is the center of this small semicircle. So O is the center of this big semicircle, and therefore AO is the radius of this big semicircle, that is 4. So in total, MO equals to AO, that is 4, minus AM, that is 3. 4 minus 3 is 1, so MO in total equals to 1. In the next step, we did a construction, that is to say, from point S, from the center of this small semicircle, that is point S, we do a perpendicular on MN. Again, from point S, we do a perpendicular on MN. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point S and MN, this point as point T. So ST is the perpendicular on MN according to our construction. whenever you have from a center of a circle or semicircle a perpendicular towards any chord, it will bisect the chord. Again, whenever you have from the center of a circle or a semicircle perpendicular towards any chord, it will bisect the chord. So perpendicular ST will bisect chord MN. Perpendicular ST is drawn from point S, that is the center of this small semicircle, and therefore perpendicular ST must bisect chord MN, according to rule 15. Repeat quickly on rule 15. A perpendicular from the center of a circle to any chord bisect the chord. In the moment we have a circle, point S is the center of this circle. Perpendicular ST bisect chord MN. Again, perpendicular ST bisect chord MN. Okay? That is to say, MT equals to TN equals to MN over 2. According to rule 15, from the center of this small circle, perpendicular ST bisect chord MN. That is to say, it divides chord MN into two halves. The first half is MT, which is of course equals to the second half of TN. Each half must be equal to MN over 2 because MN is being bisected. Repeat quickly on rule 15. Perpendicular ST bisects chord MN. The first half is MT, it must be equal to the second half TN. Each half must be equal to MN over 2 because MN has been bisected. MN is 3, therefore MN over 2 is 3 over 2, this is 1.5. So total from this long equation, we derive that MT equals to TN equals to 1.5 units. MT equals to 1.5, and TN also equals to 1.5 according to rule 15. So what is the length of this short line segment? OT. OT equals to MT minus MO. OT equals to MT minus MO. So OT equals to MT. We just write off on that MT equals to 1.5 minus M. This is 1. So OT equals to MT, this is 1.5, minus OM, this is 1. So in total, OT equals to 1.5 minus 1, this is 1 half. OT equals to 1 half units in its length. In the next step, we from point O, we join points O and S together by side line. We join those the centers of those two semicircles with each other. So from point O, that is the center of this big semicircle, we draw line segment OS. S is the center of this small semicircle. So SP is the radius of this small semicircle that is equals to X. Likewise, SQ is also equals to X. PQ is the diameter of this small semicircle. It equals to 2x. At point S is the midpoint of the diameter PQ. So at point S, OS bisects chord PQ. Again, OS bisects chord PQ into two halves. Each half equals to X. PS equals to X and SQ equals to X. So whenever you draw a line segment that bisects a chord, then that line segment will be perpendicular to the chord. Whenever you draw from the center of the circle a line segment that bisects the chord, then the line segment will be also perpendicular to that chord. And because of the fact that OS bisects chord QP, OS must be also perpendicular to QP. If OS is perpendicular to PQ, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 30. Repeat quickly on rule 30. According to rule 30, a line segment that is drawn from the center of the circle and bisects a chord will be also perpendicular to that chord. In the moment we have a circle, this is chord AB. From the center of this circle, that is to say from point O, the line segment OM that bisects chord AB. Again, line segment OM bisects chord AB according to our construction. And because of the fact that OM by set called AB, OM will be also perpendicular to AB. If OM is perpendicular to AB, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to this rule, rule 30. We already implemented rule 30 in our drawing. We have line segment OS that is drawn from the center of this big semicircle to this point O. Line segment OS bisects called QP. Therefore, line segment OS must be also perpendicular to PQ. If OS is perpendicular to PQ, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 30. So, in the next step, incorporate the right angle SOT in a new page and implement the Pythagoras theorem on this right angle OST. This is the right angle OST, this is according to the original drawing. In this right angle OST, actually we define the length of line segment OS as Y and the length of line segment ST as H. So SO equals to Y, ST equals to H according to our definition. We already found out that OT equals to 1/2. This line angle SOT by PT, according to Pythagoras theorem, SO squared, that is the square of the hypotenuse, equals to ST squared plus OT squared. SO is Y, therefore SO squared is Y squared, and it is equals to ST squared. ST is H, therefore ST squared is H squared, plus TO squared. TO is 1/2, therefore TO squared is 1/2 squared, that is 1/4. So in total, according to equation 1, we should found out that 1 squared equals to 1/4 plus H squared, or Y squared equals to H squared plus 1/4. In the next step, we join points S and N together by side line. Point S is the center of this small semicircle. Point N is the point of the small semicircle itself. Therefore, Sn is the radius of this small semicircle that equals to X. In the next step, I copy the right angle STN and equation, implemented the Pythagoras theorem on this right angle STN. This is the right angle STN, this is according to the original drawing. This right angle STN, according to the Pythagoras theorem, Sn squared, that is the square of the hypotenuse, equals to St squared plus Tn squared. Sn is X, therefore Sn squared is X squared, and it equals to St squared. St is H, therefore St squared is H squared plus Tn squared. Tn is 1.5. Tn is 3/4, and therefore Tn squared is 3/4 squared, that is 9/4. So in total, according to the equation 2, X squared equals to H squared plus 9/4. We have two equations. According to equation 1, X squared equals to H squared plus 9/4. This is according to equation 2. And according to equation 1, we already found out that Y squared equals to H squared plus 1/4. In the next step, we subtract equation 1 from equation 2. 2 minus 1. And we found out that X squared minus Y squared equals to H squared plus 9/4 minus H squared plus 1/4. We open the brackets here and we found out that X squared minus Y squared equals to H squared plus 9/4. And after we open the brackets, we have here minus H squared minus 1/4. H squared minus H squared is 0, and 9/4 minus 1/4 is 8/4. 8/4 is 2. So in total, according to equation 3, we found out that X squared minus Y squared equals to 2. In the next step, we join points O and P together by side line. Point O is the center of this big semicircle. Point P is the point of the big semicircle itself. Therefore, OP is the radius of this big semicircle. That is equals to 4, according to what we already found out in the beginning of the lecture. So P equals to 4. In the next step, we copy the right angle POS in a new page and we implemented the Pythagoras theorem on this right angle POS. This is right angle POS that according to the original drawing. According to the Pythagoras theorem, in this right angle POS, PO squared, that is the square of the hypotenuse, equals to PS squared plus OS squared. PO is 4, therefore PO squared is 4 squared, that is 16, and it equals to PS squared. PS is X, therefore PS squared is X squared plus OS squared. OS is Y, therefore OS squared is Y squared. So in total, according to equation 4, we should find out that 16 equals to X squared plus Y squared. This is according to equation 4. So according to equation 4, X squared plus Y squared equals to 16. When according to equation 3, we only found out that X squared minus Y squared equals to 2. So we added those two equations with each other, and finally found out that X squared plus X squared is 2X squared, Y squared minus Y squared is 0, 16 plus 2 is 18. So in total, according to equation 5, we found out that the 2X squared equals to 18. Here we divided this equation 5 by 2, and finally found out that x squared equals to 18 over 2 is 9, so x squared equals to 9. Our task is to find out the size of this shaded area, the size of this small semicircle. We know that the radius of this semicircle is x, therefore the area of the semicircle must be equal to pi x squared over 2. So the shaded area equals to pi x squared over 2. So it is pi over 2 times x squared. X squared is 9, so we subtract x squared by 9. So in total we can find out that the shaded area equals to 9 pi over 2. 9 pi over 2 is 4.5 pi. In terms of hours, it is equals to 14.137 square units in size. So the size of this shaded area is equal to either 4.5 pi square units in size, or in terms of numbers, it is equals to 14.137 square units in size. Okay, thank you very much.